Thank you very much for still being here, but I really want to thank the organizers. So I have the honor of giving the last talk, so now I can thank you, Lina, Akash, Sebastian, but also Tero, who couldn't make it, for this great organization, and I think we all enjoyed it here, so I have to thank you for making it happen, and of course for inviting me as well. And I should also thank all the previous speakers, because that saves me a lot of introduction, I guess. So as Sebastian already said, I'm again talking about a diode effect in a Josephson junction. So we heard that in the previous talks. But there's a big difference, and this is the fact that I want to talk about single magnetic attatoms. And you see already here, this is going to be measured within in STM. And the individual atoms are placed there, and they are going to be magnetic atoms. So since I thought that this was now the main part which is contrasting the previous talks, I first start to introduce those magnetic impurities on superconductors. But we had one talk yesterday by Chavalier, who talked about magnetic structures, also investigated with STM on the superconductor, but there he was more interested in the two-dimensional system and Shiba bands. So let me start with describing what happens if you really have a single magnetic atom, for instance, a manganese atom on some superconductor. And back in the 1960s, there had been theoretical predictions already what should happen. So you have, let's say, we start simple with just a single unpaired electron spin, and you have some exchange interaction. This gives rise to states that are inside of the superconducting energy gap. And of course, these ones you can probe with an STM in a kind of in an excitation spectroscopy mode. So now I point here to the fact that, first of all, yes, you have exchange scattering, and this gives rise to the states inside. And in an easy picture, think about it that, I mean, you have all your Cooper pairs. I'm talking about a very simple Cooper superconductor S-wave BCS pairing. And if you have this exchange interaction, you can kind of say you have a local scattering potential, so kind of you locally perturb your Cooper pair, so therefore an excitation is easier, so you can make it in the gap, you have a bound state. Now, the fact that you still preserve here some electron-hole symmetry is that because, of course, you have it on a superconductor where you always have that. However, there's also a part that's not only have the exchange scattering part, but also there's potential scattering. And for my talk, I mean, in many cases, when we talk about these U-Shiba-Rosenov states, we kind of tend to neglect it. But the expression of what is important for my talk is that this potential scattering gives rise to an asymmetry in the intensity, in the height of these states. And that will become important because of your excitation and tunneling rates later. Okay, so the first investigation was this manganese on niobium by Ali Yazdani's group. And you just saw here a small asymmetry in the superconducting gap. But since then, of course, first of all, I mean, we can go now to slightly lower temperatures. So what we are going to do is we measure at 1 Kelvin. The previous was, I think, at 4 Kelvin. And we use superconducting tips to effectively increase our energy resolution. And then typical spectra actually look like these two that I present here, and they are measured on manganese and on chromium atoms. Obviously, they are just blobs in an STM image that you see here, so there you wouldn't be able to tell which is manganese, which is chromium, but they have specific fingerprints in these U-Shiba-Rosenov states. So let me walk you through this a little bit in more detail. So first of all, I said that we measure with a superconducting tip. So that's why there's also, I mean, in order to be able to tunnel, the tip is now in the tunneling regime rather far away. So kind of single particle tunneling, which means that basically you also have to overcome this energy gap of the tip. So essentially, there should be nothing inside this energy regime. But then inside of the gap of the substrate, so we have a lead superconductor, and here, for instance, these chromium atoms, you see that, as I explained, there should be these U-Shiba-Rosenov states which are at both bias voltages, positive and negative, so we always find that, that's symmetric. But they could be asymmetric in intensity. So this is the case here, for instance, for the chromium atoms. But for instance, let me show it here for the manganese atoms. Here you have a huge asymmetry in the intensity. So we just labeled here states that we found in the gap by alpha, beta, gamma, because you actually find 3. Now, why 3? So, well, there we need to look a little bit more into the electronic structure, basically, of your atom that you place on the superconductor. Let's say, So if you say, here I just present the manganese case, let's say manganese, if you look into the periodic table, you have 5 electrons in the D shell. So potentially you have a spin 5-half system. But also if you put an atom on top of a lattice, and our substrate is an atomic lattice, then of course it's not an isotropic environment anymore. So what I try to sketch here is that you have a manganese atom, and there's only like in the surface plane, there's 3 neighbors if you sit in the hollow side, and then there's a 1 lead atom below. And this effectively leads to a crystal field splitting. So then this is sketched here. And now all these levels are singly occupied by these spins. And in this symmetry, you should actually get this threefold, these states. And therefore, you potentially can get 3 Yushi-Baruzanov states from these individual levels. And this is exactly what we see here, I've labeled alpha, beta, and gamma. And the fact that you can associate these orbitals, it's derived from the singly occupied d orbitals, but of course we are looking at very tiny energy scales, right? So you only have exchange scattering at these, and these gives rise to the states. And well, they have also slightly different spatial extent, but I don't want to go into detail here. Okay, so these are the magnetic atoms on a superconductor that, of course, you can locate with an STM, that you can spectroscopically characterize with the STM. But in the title, there was this superconducting or Josephson diode effect. And I think that I don't need to go to the details here. So obviously, we have a very simple superconductor. And just to remind you that basically what we would like to control is whether we have dissipative current or dissipation-less current. And I think I can be rather quick on this. So there has been this, in recent years, this idea that you can make this also available technologically, of course, and ideally, I mean, we've just heard it before, you can have very large rectification ratios in the sense that, for instance, if you have a superconductor which carries a super current in one direction, but a dissipative current in the other direction, then you have this large rectification ratio. Okay, so, but you have to break some symmetries, and so we've also learned that in the previous talk. So for instance, usually this is done by a magnetic field and other spatial asymmetries, of course, as well. And often, of course, what we've learned is spin-orbit coupling is important. Okay, so I think I'm the third to show this graph, so I don't have to go into detail. This is the paper back in the 2020, where you have this stack of different superconductors. By that, you have broken inversion symmetry, and then they applied a magnetic field perpendicular to the current direction. And as I said, in one direction, you can have like dissipation, while in the other one, it's still a supercurrent. And I think that Christoph explained this graph in more detail. And he also explained that this essentially then arises due to magneto-chiral anisotropy. Okay, so then Christoph also said, like, okay, you don't need to have it like in the bare superconductor or their stacks, but you can also have it in Josephson junctions. And so he showed these Josephson junction arrays, which were here proximatized to this material with strong spin-orbit coupling. And the point that he made was like, okay, you can see an asymmetry in the critical current. And as I said, the origin of it was you had this time reversal symmetry breaking by the external magnetic field. And this led to an anomalous current phase relationship. Okay, so now, as I said, we are looking at single atoms. So now the idea is, of course, I mean, first of all, it's a very different junction. It's a very different experimental setup. And you could say that, okay, basically you want to now really look into the atomic scale. And you want to see whether there, in those Josephson junctions, maybe there's also some kind of non-reciprocal behavior. So this is what I tried to show you in the remainder of the talk. So first of all, but I want to show you how, first of all, the establish a Josephson junction in the STM. Then you will see the need of that we should go a little bit away from the typical way of doing STM. So I would like to introduce the current biased spectroscopy in the STM and just show you the general results on let's call it a normal Josephson junction. It's a lead-lead Josephson junction. Then I will introduce this magnetic atoms and show you what we find. And let me already point out, we find a non-reciprocity, so an asymmetry in the retrapping current. And that is very different to all the results we've seen before, where it was in the switching, or let's call in the critical current. And then I would like to explain a little bit where it comes from. Okay, so why do we need this different technique? So let me first say, I told you that we have a lead tip, a lead sample, and when we do the spectroscopy just on this bare sample, this is the differential conductance that essentially I was showing you before already with magnetic atoms inside. So basically you have no conductance unless you hit the gap when you're far away and you have the quasi-particle current. Okay, but we want to establish Josephson junctions. So, I mean, the freedom in an STM is just great because you can approach with your tip very close to the substrate, and in that sense establish a Josephson junction. But of course, now this is what we call voltage bias because we measure still the differential conductance as a function of the applied bias voltage. Now, what you see and what's most pronounced is, of course, here that at zero bias, you have a conductance peak, and that's now typically referred to as the so-called Josephson peak. You also see that there are other peaks coming up inside of this, let's call it the otherwise when you're far away forbidden region, and these are so-called Andreev reflections, and we've also heard that yesterday how it works. So basically you try to, let's say, inject, for instance, an electron from the left electrode to the right. It can't, there's the gap, so it's reflected as a whole, and therefore you transfer kind of a Cooper pair. And so these are just at the plane junction Andreev reflections, and you can get higher order ones that you also see here in the finer structure. Okay, so that's, let's say, conventional STM, voltage bias, but I mean, if you look into your Josephson equations, basically you lose a lot about your properties of the Josephson junction. For instance, I mean, if you apply a current, a voltage, that always means that you have a change in your phase between the two superconductors. So basically then you lose a lot of your dynamics that you could learn about in the junction. So what instead you want to do is you want to have a current biased junction, and therefore now we just simply insert a high resistor in our circuit, and that effectively leads to a current bias. And why do I say that? I mean, now we can really measure basically, so we apply the current and then measure the voltage drop at the junction, and this is what I plot here. And now, well, let me walk through this a little bit more slowly. So on the x-axis now, because this is our control parameter, we have the current, and we measure the voltage drop on the y-axis. So let's say if we start at 0 and then we ramp the current, you will see here there's almost no voltage drop. I will come to that later why there's a tiny one, but let's be more it's almost 0, so this would be kind of the regime where we have a supercurrent, so no dissipation because there's no voltage drop. But at some threshold, we suddenly have a jump, and then we do get a voltage that's measurable at the junction, so that means that you measure a voltage, so that means that now you have dissipation. So now the current becomes dissipative, and this is the regime where we are, and this is usually, I mean, associated to the critical current of a junction, but now let's call it the switching current that we can measure here. Now, if you revert your biasing direction, so you go back, you see a huge hysteresis. So you remain in the dissipative part until you kind of retrap, and this is into this supercurrent part, and this is why we call it the retrapping current. Okay, now you can change the biasing direction, and obviously the same happens there, just in the opposite symmetry, so to say. So now you have also a switching current when you have this voltage drop, and then you revert, so you see a hysteresis, and you again have a retrapping current. Okay, so let's try to understand it in this model that's typically applied, and this is the resistively and capacitively shunted Josephson junction model. Why do we take it? So, I mean, basically, if we look into our circuit, we can represent it by an equivalent circuit diagram. So we have the ideal superconducting junction, which would follow the Josephson equation, but also we have a quasi-particle current that's here represented by an ohmic resistor. Then because it's a tip against a substrate, you have some capacity. And also you can have fluctuations because we are kind of measuring in an environment. And so essentially this is what our junction looks like no matter what we do. Okay, so for that we can just, then we can look at all the current passes that go through, and as I said, the superconducting junction, of course, just behaves according to the Josephson junction. Here we have the kind of quasi-particle current, which is determined by some, in the first place, let's call it an ohmic resistor, then the capacitive, so a displacement current that leads, we should write down in our junction, and finally, their current fluctuations. Okay, so if I just use the Josephson equations, then I can also write it as a equation of motion, second order in the phase. But this is just simply plugged in, and that will help later for of course for the theoretical simulations. But also you can now see how this is usually represented. So now basically we can plot here our energy landscape, and now as I've shown here as a function of this, in the second order differential equation in the phase, let's call it that we take a kind of a quasi-particle that's the phase. And so here, now if we don't apply any current, basically this phase particle is trapped in one of these minima. Now in this washboard potential, what happens if you apply a current, you tilt the whole potential. Well, maybe at this tilt, the phase particle is still trapped, so you wouldn't expect anything to happen. But of course, now you can already imagine what happens. I mean, if you tilt your potential sufficiently strongly, you kind of remove your energy barriers, and then this phase particle starts to run. And what it means is that then when it runs, you get a voltage drop, and this is exactly when we hit here the so-called switching current. Now, okay, you could say, okay, now I just tilt back my junction, and now, but why do you have hysteresis? Because now the particle was already running, so it still has the potential energy to overcome the next barrier. So therefore, it still keeps running for a while until we hit kind of a current where it goes back and it's trapped again. If there was no dissipation at all, so then basically this would only happen when you go to zero current, but it does happen before because you have also friction of this particle, and therefore you lose, of course, energy when it rolls down this potential. Okay, it doesn't matter which direction you tilt the potential, obviously, but the part that I was showing you before is that, well, but why do you then have this tiny slope there? I mean, now I was talking like as if the quasi-particle was always trapped or it was running. And well, that's due to the fact that, we deal with first of all, they're measuring not at 0 Kelvin, but at 1 Kelvin, so there are thermal fluctuations. So basically, you could eventually overcome by chance one of these barriers. Okay, and then you would say, okay, but then once you by chance have overcome it, then it should be still running all the time. But no, because you do have friction, you can actually retrap it. And therefore, you have kind of overcome a few of these barriers, but it's not completely freely running. And this is why we have this tiny slope, and this is what we call the phase diffusion regime. Okay, so why does it work? Because then actually you can't really write it down in your equivalent circuit diagram as before, but you have to kind of add another branch, and that's frequency-dependent damping, which has been nicely explained here by Kautz and Martinis back in the 1990s. Okay, so by now you also see that there's a lot of, a statistical event that comes in. I mean, you overcome these barriers also because it's thermally activated. For instance, there you see it's a matter of chance. So when you go over the barriers, but also, of course, when you tilt, the question is when it really tilts and keeps running. So if I then were to show you only one trace, that wouldn't mean very much. Instead, one should really look at histograms. So here, looking at the histograms means that we try to ramp our current in the junction back and forth a few hundred to a few thousand times, and then we always look for the retrapping current and for the retrapping current and the switching current. And we do this on both sides of the biasing directions. And here you find all the retrapping currents. So these different dark and bright green, they are the different biasing directions. They really fall nicely on top of each other, and the same do these switching currents for both directions. And you see that there's a statistical distribution, of course. Okay, so now let's say we understand the junctions, what you see, and now let's put magnetic atoms inside. So same measurement as before, that was just the plain lead junction, and now we measure on a chromium atom, let's say, which we know because we've seen the U-Shiba-Rusanoff state, so we know that we address a chromium atom. Okay, now if you look into these measurements, I mean, at first sight you would say, okay, they look similar, that's good, so you also have established a Josephson junction, you see a switching current, and you also see a retrapping current. If you look carefully, okay, the switching current is much smaller than in the lead case, and that's due to this magnetic atom inside. But what I want to highlight is that while if you look into these two biasing directions, the switching current is symmetric, but the retrapping current, for instance, is much smaller on the left-hand side than on the right-hand side. So this already points to some non-reciprocity. If we do the same measurements on a manganese atom, again, I mean, roughly speaking, you have the hysteretic curves, you see the switching currents, and you also see retrapping currents. And now, again, the switching are symmetric, positive and negative biasing directions, but the retrapping currents are not. And now it's exactly the opposite asymmetry. So now you have the smaller retrapping current on the positive biasing direction. So first of all, this means we have non-reciprocal behavior. It's only in the retrapping current, or it's mainly in the retrapping current to be precise. And it's opposite for manganese and chromium. And as I said, we should do statistics and not just pick out one trace. So I really want to convince you. So this was the statistics of the pure lead junction. And everything was falling nicely on top of each other depending on biasing direction. Now in chromium, you really see that these histograms of back and forth, they are very much shifted, and the same is the case for manganese and exactly in the opposite direction. And there's only a tiny little bit of asymmetry in the switching part. So this is what we could also call diode behavior, and usually you would like to ask, okay, how can you tune it? Well, again, we can have this freedom of the STM tip coming closer, so basically you change your Josephson coupling energy. And here we put this as a function. We now use the phase diffusion as a measure, but basically you can also say, well, we use the junction conductance in the normal state, but this actually is nicer and more precise because we know exactly the junction. So all the switching currents, they fall on top of each other back and forth. In the retrapping, you see the asymmetry here for chromium, here for manganese, and you see that this, it's opening this fan. So actually, the larger is your conductance, the closer you are, the larger is the asymmetry. Okay, now the question is, where does it come from? And now I want to say, okay, wait, it's in the retrapping current, so there must be some symmetries, again, broken, and something, retrapping is mostly like you retrap your phase particles, so this has to do with friction, right? So maybe it's also, like, intuitive to look for signals which may be affected by retrapping, so by friction. So now let's go back to our differential conductance spectra, U-Shiba-Rusanoff states, and I remind you of this electron-hole asymmetry that we had. Well, there the tip was far away, and now I could at least ask already, well, there was an asymmetry, and now we see an asymmetry also in the Josephson, in the retrapping current. Maybe that's connected. But for that, at least we should go close with the STM tip and have also a junction, a Josephson junction established in the regime of where we see these type of tunneling processes. But now I would still go to the voltage bias junctions here. So just here, this was tip far away. We come close. So what you notice, I mean, of course, there's this Josephson peak. And then there are these Andreev reflections. So gray is the background comparison spectrum. But then you also see that there are additional peaks on top. And they are, again, asymmetric in intensity. So you see it here very pronounced. I mean, if you look into the same bias voltage, positive, negative, you see that there's a huge asymmetry. Okay, where does it come from? I mean, again, of course, these U-Shiba-Rusanoff states have to be at the origin. And let me just say that, I mean, we don't only have plain Andreev reflections at the bare gap, but you can also have, let's say, for instance, you try to inject an electron from this side, it will be reflected as a whole. And here now at this side, it can resonantly, so to say, excite one of these U-Shiba-Rusanoff states. So this is what we refer to as resonant Andreev reflection. And you see also that this transfers, I mean, it's a quasi-particle tunneling current again. And of course, you can have higher order processes as well. So, well, that already, I would say, intuitively points to the fact that, okay, so you have kind of a tunneling process that's exciting your U-Shiba-Rusanoff states. It's a quasi-particle current. And the quasi-particle current has something to do with this dissipation, of course, and that already relates to the Josephson non-reciprocity in the retrapping. But let's go and try to understand it in more detail. And for that, we had this theory collaboration with Felix von Oppen and his PhD students Jakob Steiner and Larissa Melischek. But actually, what they put in the model, basically, they have to calculate or solve this differential equation that I was showing you before, but which parameters should they put inside? And so in order to do that, we just take the experiment. Instead of looking at the differential conductance, we can also extract the tunneling current immediately. And you see, obviously, now we plotted here for the two bias directions. You see there's an asymmetry, as of course expected from the differential conductance. And you also see an asymmetry for the manganese, of course. So now, with this current voltage relationship, you already see, I mean, this is far from being anything that's like an ohmic resistor. You already see that basically your current, because it goes through these U-Shiba-Rusanoff states, is very much voltage dependent. So basically, in this equation where in the RCSJ model we had an ohmic resistor, it's by far not an ohmic resistor, but we can now extract this resistor, which is voltage dependent, just from the experiment and put it into the calculation. So they solve this by Monte Carlo simulations. And this is what they get. So here for these two current voltage curves that are extracted from the experiment, you see that they find switching and retrapping currents. They find that they are highly hysteretic. And also, if we look into that, the retrapping currents are highly asymmetric, and they reproduce exactly the thing that we find in experiment, the opposite behavior for manganese and chromium as it should be. Okay, so now in this case, we have a diode behavior. Contrary to earlier experiments, we find it in the retrapping current, not in the critical current, not in the switching current. We did not have a magnetic field to break time reversal symmetry, but we don't need that because in the retrapping current, it's kind of even more like the semiconducting diode. It's in a, it's in a dissipative channel, and therefore you just need to break electron-hole asymmetry, like you also do in a p-n junction in a way, but by these U-Shiba-Rusanoff states. Okay, so with this, I would like to sum up. Well, we can create atomic scale Josephson junctions, of course, in an STM. We can effectively current bias them very simply by adding a resistor. And then we preserve, somehow these current phase relationships that you expect for a Josephson junction, such that we can look at the dynamics and look at, switching and retrapping currents. And we find then an asymmetry that we can explain by the electron-hole asymmetry that stems from the U-Shiba-Rusanoff states. And I don't want to end without the most important part, namely thanking the people who did the work. And this is, in my group, it was Martina Trams, so she did her PhD work on that. And I tell you this with these hundreds and thousands of sweeps, and that you need to get the nicely stable conditions and make sure that this is really related to the U-Shiba-Rusanoff states. It was tremendous work of her. Without her patience, I think we wouldn't have gotten there. Then Bharti Mahendra was joining her first as a master student, now continuing the project. And as I said, this work profited a lot from the collaboration with Felix von Oppen and Larissa Melischek and Jakob Steiner. And I thank you for your attention.